This is going to be example 3.2 from the OPENSTAX textbook. And so we're talking about chapter 3. We are beginning two-dimensional kinematics. So let's look at this example. First, let's erase this mess. There we go. Gone. So now let's read through the question. Use the graphical technique for adding vectors to find the total displacement of a person who walks the following three paths. So we're looking for displacement. So we're adding vectors and we want to do it graphically. All right, let's keep on going. First, she walks 25 and 0.1 of a meter in a direction 49 and 0.1 of a degree north of east. Then she walks 23 and 0.1 meters heading 15 and 0 degrees north of east. Finally, she turns and walks 32 and 0.1 of a meter in a direction 68 and 0.1 degrees south of east. Okay, so let's just start by putting our coordinate grid up here. So I'm going to start here and draw a line that way, close enough to straight. That'll work. And then I'm going to put another one over here and then over here. Okay, so this is obviously not going to be perfect, right? Because I'm freehand drawing this, and I'm not even using a ruler, actually. So now that I kind of used some cheating with the program, but it's not going to be perfect, and it's going to be even less perfect than it would be on paper, but this will get you the idea of how to do it. So let's walk through these from the beginning. So first, she walks 25 meters in a direction 49 degrees north of east. So 49 degrees north of east. So how do we find that? Well, we head out east. So this is going to be east out here. And this is going to be north. We use these on the coordinate grid just like they are on a compass. So this is going to be east, this is going to be north. So this would be north of east. 49 degrees is just a little more than 45 degrees. So 45 degrees is right halfway between 0 degrees and 90 degrees. So we're going to draw it just a little bit more than that. And for our first drawing, we're going to just do an arbitrary 25 meters. Okay, so we're going to draw this out here, and we're going to say that this is 25 meters. So this is 25 meters. All right, easy peasy. Now we'll go ahead and label our angle as well. I'm going to put it kind of labeled down here so we have room for other things. So this angle right here is 49 degrees. All right. So then she walks 23 meters heading 15 degrees north of east. So 23 meters would be just, so the line, our magnitude of our vector is going to be just a little bit shorter than this. I'm going to try to draw it basically the same size. Oh no. Sorry, but life happens. So anyway, so to figure out 15 degrees north of east, so north of east, now we're talking about here, but in order to draw that right, it has to be from this new reference. So what I like to do is I like to kind of dot in a coordinate grid. Again, this isn't perfect. I'm drawing this with a tablet. It's going to be the best that we can do, right? So it's still 15 degrees north of east, but we look at it in reference to here. So 15 degrees north of east would be just a little bit up right here. So let me get my orange back. And so it's going to be about like this, about 15 degrees. And it's about the same distance, right? So something along those lines. This magnitude here is 23 meters, right? 23 and 0.1 meters, if you want to get the significant figures right. And this angle right in here, I may change to a different color so it's even more clear what I'm doing. Right in here, this angle is 15 degrees. Now, finally, she turns and walks 32 meters in a direction of 68 degrees south of east. So this time we're going down south of east because this is south down here. All right, so she's going to turn and she's going to go there. So let's draw a little reference coordinate grid right here, right where we ended up. Okay, So she turns 68 degrees south of east. So south of east, so 68 degrees is still less than 90 degrees. So we're not going all the way to negative 90 here, but it's steeper than this one over here. Okay, so it's closer to that, maybe even a little further, and it's a longer line. Oh, let me erase this E. Excuse me, wrong tool. Let me erase this E there so it's going to be a little bit clearer. So it's going to be a little bit longer. Now, this sketch, and I mean sketch, this is a rough sketch, is even less accurate than what you should have on your paper, because you can actually use a protractor and you can measure things to where this one is about the same distance to this one, but a little less, and this one's even further, and so you can get even better ideas. But this is the basic core idea. This was what, 68 degrees. This is the basic core idea. Now, we're not quite done because that's what she walked. But in order to add these vectors, we use the tip to tail method. Now, we already have the vectors laid out tip to tail. So we've got tip to this tail and then tip to tail. They're already laid out in a row. So once they're laid out tip to tail, all of them stuck together, then the added vector is from where we started, the origin, to where we finish. So it would be this vector right here. Now, this may not be exactly perfect of what this really looked like, but from our sketch and with the detail we have, this is as close as we're going to get. So this is our final displacement. So this is our it's not just our delta x, right? Because our delta x is just from, let me even get a different color. Our delta x is just from here to here in the x direction. Our delta y is let's change to something bizarre-ish, not too bad. Get I don't know, something way different. How about a lime green? That'll show up. Whoops. Oh my gosh, I'm hitting wrong colors. That's okay. So the delta y would be from here down to here. So this is our delta y, our change in y. Now these two together make up the displacement vector, which is this red one that I had. So it's all of this together. All right, that's the end of this example. We'll see you for the next one.